question in this tutorial is, how is scientific work different than our everyday definition of work? To begin, let's look at our everyday definition of work. Our everyday definition is very broad sense. It could be mental or physical. It could mean anything from doing yard work outside to doing schoolwork or a job that we have. Scientifically, work is very specific. It is only the physical aspect of it. Work occurs scientifically when you do two things. You must apply a force, and it must move because of that force. So in this situation, doing your schoolwork is not a scientific type of work. You must apply a force to something, and it must move. For example, if we apply a force to a shopping cart, we apply a force, and it moves across the floor. Scientifically, that is going to be work. If we lift up a heavy object and we just hold it there, the idea of just holding it still is not scientific work, because the object is not moving if we simply are holding it still. Also, if you were to push against the side of a room, maybe push against the wall, scientifically that is not considered work because the wall is not moving. You might be exhausted after a while if you're holding that heavy object or you're pushing against the wall for an extended period of time, but scientifically you're not doing any work unless the object moves. Now, there can also be situations in which the object moves but there's no force. For example, let's look at a comet moving through space. If there's no planets around to give a gravitational force, that comet is moving through space because of inertia. There are no forces applied to the comet. And so therefore there is motion, but there is no force. And so there is no work done on the comet as it moves through space. So again, you must have two things. You must have a force and you must have motion. Therefore, if we look at our equation for work, we can see that work is the force times the distance it moves. So again, you have to have that motion and you must have that force. So the question is, why is there a cosine of an angle in there? And what does that angle represent? Let's say, for an example, we're pulling something across a level floor. So here I've got a skateboard and I'm pulling by a string with some unknown force. Now that string being pulled here, it's going to make this skateboard move horizontally across the floor. And we're pulling up at an angle of theta. Now the force itself, all of this component of the force, or all this force, the hypotenuse I should say, is not causing the motion. Only the horizontal component of the force is causing the motion of the skateboard. The vertical component of the force is not causing any motion. So when we talk about the work done, what we're looking at is the work is really just the x component of the force. It is really just the part of the force that causes it to move times the distance that it moves. Now, we are never given this just component of the force. Instead, we're given the hypotenuse itself. And so how is this component related to the hypotenuse? Well, it is related through the cosine, because this is my adjacent side, this is my hypotenuse. And so the relationship between the two is the cosine of the angle is equal to the adjacent side divided by the hypotenuse. If I solve for the adjacent side, f sub x, by multiplying f on either side, I get that my x component is equal to the hypotenuse force times the cosine of the angle. And so what we're going to do is we're going to replace this component with the actual force itself times the cosine of the angle, then we have times the distance. Usually we write our trig functions at the end, and so we get that the work is equal to the force times the distance it moves times the cosine of the angle between them. So when you're looking at the angle, you're looking at the direction of the motion, the direction of the force, and we want the angle between those two. We want the angle between the direction of the motion and the direction of the force. Now, work is considered a scalar, meaning it has no direction. Other examples of scalars were things like mass, volume, temperature, speed, distance. These are all considered scalars. None of them have direction. The unit is considered something called a joule, named after a scientist here, James Joule. It is actually an abbreviation of a force, which is a Newton, times a distance, which is a meter, and we abbreviate that as a J, or joule. The funny spelling, again, is because it's named after a scientist. Now, although it is a scalar, work can still be positive or negative, just like temperature can be positive or negative, even though it has no direction. So what does it mean for work to be positive? Well, work is positive when the force and the distance are in the same direction. Maybe not exactly the same, but relatively the same. Like, for example, this situation here. The motion is to the right, and the direction of the force is more right than it is considered to be left. So in this case, it would be considered positive work. They are roughly the same direction. This means that the angle is anywhere between 0 degrees and 90 degrees. In this situation, the object will speed up. We have negative work if the force of the distance it moves are in opposite directions. So in this case, we have like if we are slowing an object down, you have, let's say, a grocery cart moving, and you push it to slow it down. That is considered negative work. The object slows down. This would be an angle between 90 degrees and 180 degrees. Now notice I don't have it including 90 degrees on either end. That is because if the angle is at 90 degrees, that means that we have 0 work done. In this situation, the object is being carried. So again, even if you're carrying a heavy stack of books, you're not doing any scientific work. Remember that scientific work is very different than our everyday definition of work, in that the force is going to be upward, but the motion is to the left or right. It is horizontal. And so no work is done when we're carrying an object. You might say, well, wait a minute, don't we have to apply a small force forward to get it moving? And so don't we do a little bit of positive work? And we do. We do a little bit of positive work to start it moving. But as we carry it, then we eventually stop, which means we apply a little bit of negative work to stop it. And it just turns out that the little bit amount of positive work that we do to start it moving and a little bit of negative work we do to stop it from moving cancel each other out. And so the overall effect of any object that's being carried is that 0 scientific work is done. So again, for scientific work to be done, you must have a force and it must move. It is a scalar, but it can be positive or negative. Positive if it's in the same direction and the object speeds up. Negative if the force and the movement are in opposite direction and it slows down. And 0 work if the object is being carried, if they are perpendicular to the motion in